Okay, so let us get it going. Good evening, everyone, especially the very young students who came all the way from various places in the city, probably from suburbs in this monsoon period. So it really shows the kind of interest on this particular lecture. Today's speaker is Professor Srirup Ray Chaudhary. Many of you know. Not only from within the institute, but also those from outside. He is one of the well-known theoretical physicists that the country produced. He is going to talk on such a nice, interesting, you can actually see the slide that says it all with the frame, golden frame around, on the early history of particle physics in India. And those of you who are here in the auditorium need not, I'm sure you know that the particle physics, the physics of cosmic rays and elementary particle physics has been the main interest of research topic subject even to Homi Bhabha. So I'm sure Srirup is going to take us through all these milestones and important contributions of Indian scientists to the particle physics. So without taking more of your time, I would like to invite Professor Amol Dighe to introduce today's speaker. Amol Dighe, of course, is also a well-known theoretical physicist this country has ever produced, and he is the Dean of Graduate Studies of TIFR.
So, welcome again to you all. It's a pleasure to introduce Professor Srirup Ray Chaudhary. Of course, most of you sitting in this audience perhaps don't need any introduction to him, but I understand that this program is going live on YouTube and Facebook, so I think people should know a bit about him. He is, of course, one of the well-known theoretical particle physicists in India, but compared to these early days, he actually came on the horizon quite late. So he did his PhD from the University of Kolkata, and he was a postdoctoral researcher in TIFR and later on at CERN in Geneva. He then joined IIT Kanpur and was there for many years. However, at some point of time, we did manage to snare him off from there and bring him to TIFR. He is, apart from being a very good particle physicist, he's also known as a very good teacher and a very good speaker. And I'm sure you will enjoy his talk. Without coming between you and his talk, let me invite him and let's enjoy the talk. Welcome, Srirup.
So thanks, Amol and Satya, for that very warm introduction. So, and I'd like to thank all of you in the audience for coming here to listen to this topic, which is not part of your everyday research or not part of your things, but it has to do with things in the past. But of course, interesting things in the past, as I hope to convince you over the next a little more than an hour. I'll tell you about the way particle physics, cosmic ray research and so on started in India and how it was taken ahead. And before I start, let me start with a disclaimer. There is no original research in what I'm going to tell you. All I have here is well-known material. It's mostly taken from the internet. There are only 3 pictures which are not downloaded from the internet, but the rest of the material is there. But in true Make in India style, I have put the package together, and I hope you will like the way it is presented. So without more ado, let me take you back to somewhere around the year 1900. So at that time, I'm sure you know that there was an entity called the British Empire. And this is the dark brown sections all over this map. And here, this was the center from which it was ruled, and we lived somewhere, okay? Well, our ancestors lived somewhere along this region. So all the science which was happening, the Western science or the origins of particle physics, happened in this area, and from here it had to come here. Now in those days, it was not the days of internet and Google and so on. So if you had to learn about those things, you had to make a long and arduous voyage by ship. So you would go typically from Bombay to Karachi via Aden, through the Suez Canal, then through the Mediterranean. It was more than a month's trip, and then right along the coast of Africa, around through the Straits of Gibraltar, and then you went up through the Atlantic Ocean and you reached England. From there you took a train and you reached Oxford or Cambridge or London or wherever you wanted to. So it was not, things were not easy. It was a difficult thing to go there, just to go there and come back. And of course, it was also not here to learn new things. So let me start the story, go back a little bit, because particle physics research grew out of nuclear physics. And nuclear physics essentially started with the discovery of radioactivity. So I'll just take you quickly through the important milestones there. In 1896, Henry Becquerel discovered radioactivity through the fact that uranium salts. I mean, all this is known to people, of course. In 1898, Gerhard Schmidt and Madame Curie discovered that thorium is also radioactive. It has the same effect. And then Pierre and Marie Curie discovered both polonium and radium. And Madame Curie's thesis had the name radioactivity, which we use so commonly. In 1899, Rutherford discovered alpha and beta rays. He was in Montreal in those days, and he invented the concept of half-life. Paul Villa in 1900 discovered a highly penetrating radiation, which we today call gamma rays. In 1902, Rutherford and Soddy at Montreal suggested that radioactivity involves disintegration of atoms. Okay, in those days, atoms were thought to be indivisible. This is Soddy here, a young version. Rutherford and his student Thomas Royds, well, this is a picture of him when he was not a student, and it proved that alpha rays are just doubly ionized helium atoms. It's a very beautiful experiment, which I'm sure you learn. Soddy and Casimir Fahans, whose name many people do not hear, discovered the radioactive displacement law of how things, alpha and beta ray change elements, move them around the periodic table. And Soddy and his student Ada Hitchens from Aberdeen discovered the existence of isotopes. Now you may wonder why we have this silhouette here. That is because I searched the internet high and low, and I couldn't find any picture of Ada Hitchens. I could find a picture of her matriculation certificate, but that's not the same thing. Okay. Now, where did radioactivity research start in India? You may be surprised to know that it started in this very city, and it started in St. Xavier's College. So St. Xavier's College, this is how it used to look around the late years of the 19th century. And here, in around between 1910 to 1911, there was a Jesuit father, Father Adolphus Steichen, who was a German by birth, and he had graduated from Göttingen and studied physics there. So he was the professor of physics at St. Xavier's College, and his colleague, Father Shep, was also the professor of chemistry. So between them, they went to, actually it's near Godhra, and they studied the radioactivity of hot springs there. Again, I could not find a picture of these two Jesuit fathers, so we have just something symbolic. Okay. So if anyone in the audience has access to any of these pictures, which are not here, I'll be very grateful if you could let me have them. Okay. Now, why radioactivity of hot springs? Because in those days, people didn't really know where radioactivity came from, why it was happening. So there were all sorts of theories. And a Professor Ramsay of Indiana University, he had claimed, so this is the only very grainy picture of Ramsay I could find. He had claimed that the radioactivity of hot springs increases when the flow of water increases, and it decreases when it falls. Now, what Father Steichen and Shep found, he found the exact opposite at Tua. And they attributed it correctly to saying that, okay, the reason is that there is some radioactive rock, which is solid, and the spring is leaching out that water, and therefore when the water flow increases, the amount of radioactive material is diluted, so you see less. So they had the correct explanation, whereas Professor Ramsay's results must have come from a place where the increased water was also washing out more material. So we can guess that now. However, so you may think these results are trivial, but in those days they were really surprising things. So their paper, which came out in 1916, so you may wonder what happened. If they did the work in 1911, why did the paper come out 5 years later? And the reason is that in the meantime, the First World War had broken out, and both of them were German nationals. So they were put in an internment camp near Nainital as enemy aliens. And it was from there that they obtained permission to send the paper. It had to go via the sea route. And of course, during wartime, everything was censored. Anyway, eventually they managed to publish it. So I'm telling you this story because I'll have the opposite story to tell soon. Later, Father Steichen was given a grant to study the hot springs in the Madras Presidency, as it then was, which is most of the south of India then, from 1918 to 19. This is a 5-year project. And we have a memoir that he was given a grant of 1,000 rupees to do this. So 1,000 rupees was supposed to cover his money. It was supposed to cover the cost of hiring assistants, travel, stay, equipment. Everything was to come within 1,000 rupees. So also this tells you how far 1,000 rupees would go in 5 years in those days. I want you to particularly remember this figure because I'll show you some other figures as we go ahead. Okay, well, this was not the only place. The other place was the newly formed Indian Institute of Science. Again, this grainy picture shows you how the original building looked. It still looks much the same. So in 1914, Herbert Watson, who was a young assistant professor at the ISC, he conducted a study of radioactivity in the rocks along the Kolar township and gold mines. So if this is Bangalore or Bengaluru, this is Kolar. It's not far away. The mine is fairly close. And these are some of the oldest rocks in the Earth's crust, which belong to the Gondwana block. And the gold mines were then providing samples from about 4 kilometers down. So they wanted to see whether if you go into the interior of the Earth, will you find radioactivity? So the work of Watson was helped by his assistants, Gosto Biharipal and W.F.S. Smith, who was in the geological department. Again, I couldn't find pictures of them. But they didn't find any radioactivity in these rocks. And their negative results were first published in the Proceedings of the Indian Academy of Science, which came out from ISC, and also in the Philosophical Magazine in the year 1914. So there were negative results. They just said that when we went to, we didn't find any radioactivity. Later, Watson left India. 2 years later, he joined the University of London as professor of chemistry, and they say that he invented neon lighting independently. But that's a different story. But of course, once he had left, these people also, Smith went back to his geological studies, and Gosto Biharipal went back to Kolkata, where he wrote a famous textbook of chemistry. Okay, now, of course, there were further developments in nuclear physics as the years went by. So between 1908 and 1910, as you know, Geiger and Marsden, Rutherford students, made a lot of observations of alpha particles. Everyone studies this in their coursework. And Rutherford explained that this can be only explained if there is a nucleus. So it followed that the new hydrogen nucleus was the first elementary particle to be discovered, and you call it the proton. Niels Bohr in 1913 explained the atomic line spectra using the new quantum theory. Moseley proved that the charge on the nucleus is equal to the atomic number, so supporting Bohr's theory. Rutherford in 1920 had some inkling of the fact that there is something called the neutron, but the real proof came from Dmitry Ivanenko, 1931, who predicted the neutron based on quantum mechanics and using the idea that beta electrons cannot stay within the nucleus. They must be produced at the moment by a neutron decay. And in 1932, James Chadwick discovered the neutron. So all this is textbook stuff. What happened in India? So I couldn't resist showing you this iconic picture. So this is Sir J.C. Bose in the center, and around him are some of his students who all became very important scientists in early India. Meghnad Saha and S.N. Bose you have heard about. J.C. Ghosh was director of ISC, also first director of IIT Kharagpur, founder of the IIT system. Snehamoy Datta was a spectroscopist. Nikhil Sen, general relativist, also well-known colloid chemist, and also a well-known soil chemist. So these people sort of were the pioneers of starting science in India. But the person I want to concentrate on among them is the one whose name I didn't read out. That is D.M. Bose, or Sir Devendra Mohan Bose, who was J.C. Bose's nephew. All right. So this is the picture on the poster. So D.M. Bose is how he used to look as a young man. And the story really starts with him. So in 1907, he sailed to England and he enrolled himself at Christ's College, Cambridge. Now, you have to remember that in those days, there were no postgraduate departments in India. All the colleges used to teach undergraduate up to bachelor's, and to do a master's or beyond, you had to go to England. There was no other way, or some other country. So D.M. Bose went to England and enrolled in Christ's College, where he was fortunate to have some very good teachers. One of them was Sir J.J. Thomson, who discovered the electron, and one of them was C.T.R. Wilson, who invented the cloud chamber. Now, Bose's inclinations were always towards experiment, and therefore it was Wilson's work which really excited him. So here is a picture of the actual cloud chamber built by Wilson. So it was this tiny machine, and this was Wilson's cloud chamber. And this is the kind of picture they could take in 1911. This is some radioactive decay happening, and you see some charged particles coming out of that. This is very sort of indistinct and grainy pictures, but that's how it started. So, having done his studies there, D.M. Bose returned to India and joined the City College as a lecturer. Here's a sketch of the City College as it used to look in those days. It still stands. There are many buildings which have come up around it, so it doesn't look quite the same. But in 1914, he was appointed the Sir Rashbihari Ghosh Professor of Physics at the new Department of Physics at the University of Calcutta. I have to tell you a little bit about this. So the University of Calcutta, like other universities in India, did not have any postgraduate program. So around that time, they had the first Indian Vice Chancellor, Sir Ashutosh Mukherjee, and he was originally a mathematician, then discovered that he could not make enough money doing mathematics. So he studied law and became a lawyer, made a lot of money, and was also made Vice Chancellor. But he wanted science departments in university. So he founded departments of physics, mathematics, chemistry, and what it was called then, I forgot, biology, just biology. And he, of course, he had lots of friends among the lawyers. So from other lawyers, he was able to get some money to run these departments. So Sir Rashbihari Ghosh, who was an eminent lawyer and became a judge later, he donated more than 21 lakh rupees to Calcutta University for this purpose. Now remember, this is the same period at which Father Steichen could run a 5-year project on 1,000 rupees. So it tells you how generous the grant was. It also tells you that I'm sure Sir Rashbihari Ghosh did not give all his money to the university. So he must have had a lot more. And it also tells you how much money was made by lawyers in those days. Okay, so, all right. Well, it probably still holds true. Okay, now one of the things which came with this Ghosh professorship was that it came with a travel grant. So there was a traveling fellowship for 2 years, during which the Ghosh professor was supposed to go somewhere abroad and learn new skills and come back. And D.M. Bose immediately decided that he would go to Berlin and to the laboratory of Erich Wegener. Now, very few people here will remember or will have heard of Erich Wegener, but Erich Wegener was a professor in the Berlin Agricultural University, but he was one of the early pioneers in cosmic ray fluxes. So here is a quotation from Bruno Rosi, the Nobel laureate. I won't read it all, but he says that the measurement was brought to an unprecedented degree of perfection by the German physicist Erich Wegener and his group. So this was one of the leading groups, and Bose wanted to go there and do his stuff, learn cosmic ray measurements from here. Now the interesting thing is this was 1914, and cosmic rays had only been discovered in 1912. So despite the distance, despite the difficulties of communication, he was very much up with the time. So he was interested in cosmic rays within 2 years of this happening, and he wanted to be part of the measurements and do some of the current work. So he went to Berlin. And now the opposite problem happened, which was that the First World War broke out, and now it was, remember, India was under the British, so Bose was a British subject. So now it was his turn to become an enemy alien. However, at that time the Germans were treated him better. They did not put him in an internment camp, which is very different from what they did with people later, but he was only required to report regularly to the police, and they allowed him to carry out his research work. So he was able to continue his work, and what did he do there? So he managed to build a cloud chamber. So he built a better cloud chamber than Wilson's, and by that time some things had progressed. And with this cloud chamber, he was managed to record the recoil tracks of particles. So you take fast alpha particles. So from this grainy picture, they concluded, I'm not really sure how to read it, but they could at that time. So you had fast alpha particles hitting nuclei, and a host of hydrogen ions would come out from that. They would leave these tracks, and this is the first time you showed that there was recoil of the nuclei. There was recoil from the hydrogen, and so it proved that in some sense that momentum is conserved at the atomic scale. And in some sense, this was also what prompted the beautiful work of Compton when he explained photon electroscattering using momentum and energy conservation. So for this work, Bose was awarded a PhD by the University of Berlin in 1919. So you may ask what he was doing there in 1919, because the Bose fellowship was for 2 years. The point is that it was a wartime, so he could not leave Germany. He could not come back to India. So he was stuck in Germany till the end of the war. And he used it, well, he used it to do his PhD and get it from the University of Berlin. And actually, he used his time very well. So he went to listen to the lectures which Max Planck used to give every Monday at the Kaiser Wilhelm Institute. And he really liked the lectures. He said, after attending Planck's lectures, I learned what a system of physics meant in which the whole subject was developed from a unitary standpoint and with a minimum of assumptions. But Bose was not the only person listening to Planck's lectures, and others did not have the same kind of response. So here is another one. So clearly, it did not appeal equally to everyone. Okay, so now let's come back to India. So in 1919, D.M. Bose returned to Kolkata, and he resumed his position, and this big building had come up by then. This is today is the Rajabhaja Science College, but it was the University College of Science. It had come up in those days. So he resumed his position as the Rashbihari Ghosh professor from 1919. But now he had a colleague who was also a chair professor, and of course you know who that was, C.V. Raman. And C.V. Raman, as you know, was a former civil servant. He was to work in the Audit and Account Service. But in 1917, Sir Ashutosh persuaded him to abandon that job and join the university and take up an academic position for half the salary. Okay. Of course, you may want to know what the salaries were. So in the Audit and Account Service, he was paid 2,000 rupees a month. And as Palith professor, he was paid 1,000 rupees a month. But of course, you know what 1,000 rupees was worth in those days. Okay, certainly far more than any professor makes today. Okay, but in those days, the early days of this university, at that time, it was really stellar. So you had other people like S.K. Mitra, who conducted this beautiful research on the ionosphere, conduction of radio waves. S.N. Bose, all of you know what he did. B.B. Roy, who was a noted spectroscopist who worked with Bohr, with Hertzberg and others. M.N. Saha, cyanization formula. So it was a really stellar department. There was also P.C. Mahalanobis at the Presidency College, who was also teaching university courses. I mention this in particular because today is the 125th birthday of P.C. Mahalanobis. Okay. So Bose came to Kolkata, and he started working on what he knew best. He built a cloud chamber with the help of his assistant, S.K. Ghosh. Subodh Kumar Ghosh, again, no picture exists. This is just an imaginary picture. But they were able to publish their work in Nature. So they published some work. This is also from Nature. And he talks about his work, and we have obtained a few photographs and so on. So now he's looking at the recoil not of hydrogen, but of the helium ion. Okay. But these are not the only people. So now physics was beginning to start in other places. So M.F. Soonawala, again I couldn't find a picture, but he wrote a paper in the Indian Journal of Physics. It's a very interesting paper. So he was in the Maharaja's College of Jaipur, and his paper, he suggested that all nuclei can be made up of electrons, of course, protons, and noble gas nuclei. So today, if you replace the noble gas nuclei, they have the closed shells. So you put protons around them, and you keep building up till you get the next noble gas. And so it's a sort of very rudimentary version of the Aufbau principle, which everyone learns, and how, or the nuclear shell model, if you like. So he had some similar idea, and he published it in the Indian Journal of Physics. So people were actually publishing very nice work there. There was A.C. Banerjee, Amulya Banerjee, who had passed this notoriously difficult exam called the Tripos from Cambridge. People who passed that were called wranglers, and he was a wrangler, and he came and joined Allahabad University, where Meghnad Saha had also moved from Calcutta University, and they were the first Indians to apply quantum mechanics to the study of nuclear spectroscopy. So pioneering work in those days. There was a third person, B.M. Sen, who was also a wrangler from Cambridge, but he wrote a number of papers in Nature and the Philosophical Magazine on beta rays. So he was trying to apply relativity to beta rays. Relativity was very new in those days. And one of the nice things, he proved that the neutron is a Dirac fermion. He gave evidence to show that. We now take it for granted, but it was not for sure in those days. So he was in Rajshahi College, which is now in Bangladesh, but was part of undivided India in those days. And this is a portrait. Actually, this is a photograph of an oil painting of B.M. Sen. It's the only picture I could find of him. And I'm indebted to a colleague in Presidency University for sending me this picture. It's the only one which I know exists. So why it's in Presidency University? Because B.M. Sen later came to Presidency College and became its first Indian principal. Okay. Now, out of all of this nuclear physics came the first paper, which I would call a particle physics paper. And this was written in 1933. So Meghnad Saha had moved to Allahabad University as a professor, and D.S. Kothari was then an MSc student. So MSc students do MSc projects. So his project work, which had been given to him by Saha, was to explain the continuous energy distribution of the beta rays emitted from a radioactive nucleus. Now we all know this, that if a neutron decays to a proton and an electron, the energy of the electron will be fixed, essentially by the mass difference. It should be about 1.2 MeV. It should be somewhere around, 1.2 electron volts. Here, MeV, that's right? MeV. It should be here. However, so there is a 10 to the 6 here. However, we know that it's all over the place, as you see in this picture. So they set themselves to explain it. Now, of course, this was 1933. So Pauli's idea that there's a neutrino which takes away some of the mass, which is the correct idea, had already been proposed in 1930. But at that time, nobody believed Pauli. People were not so willing to accept new particles as they are today. People were much more conservative, and it was thought to be some crazy idea of Pauli's. Now, the idea of Kothari and Saha was actually very nice. So they said that every beta decay process is actually a gamma ray emission from an excited nucleus. Let me show you a cartoon of how this happens. So imagine that this is a nucleus, excited nucleus. It emits a gamma ray, which immediately in the field of the nucleus, there's a pair creation of an electron and a positron. Now, the electron goes out, the positron goes out, the electron is absorbed. Or it can be the other way around. So at a certain unknown amount of, so I'll just repeat this, a certain unknown amount of momentum goes into the recoil of the nucleus, which you cannot see. So you will have a distribution of energies for this particle coming out. It's a very cute idea, and it's also helped by the fact that almost every beta decay is accompanied by a gamma decay after that. So if you see a sample, radioactive sample, you will see both beta and gamma decay happening in the same sample. So you cannot tell which came first and which came second. So this is a perfectly good idea by the whatever was known at that time. Okay, I've just said this. And of course, it didn't require a neutrino. So, but in 1934 came Fermi's theory of beta decay, and that gave a particular shape for the energy spectrum, and that was vastly different from the energy spectrum measured by Curry in 1936. So the Curry plot, so this is some version of the Curry plot. So the distribution expect from the Saha plot would be like this. This thing will not happen unless you use the Fermi theory. So that basically killed the Saha-Kothari theory, but it was a very nice theory, and certainly Kothari's MSc project became a paper in Nature, which doesn't happen for most MSc projects. And after that, he went to work with Rutherford, which also doesn't happen for most MSc students. Okay. Now, I'll change to a different track and tell you the story of Max Born and India. So, as you know, in 1933, same year as all this was going on, Hitler came to power in Germany, and with the Nazis, they started persecuting Jewish scientists. They were all dismissed from their jobs, so the Jewish scientists started escaping wherever they could. Okay, some to England, some to France, some to Russia with bad effects, of course, most of them, and various places. So they started running away. So out of the people running away, C.V. Raman thought here is a good opportunity to get some good scientists to India. So he tried hard to catch Erwin Schrödinger and Max Born. Now Schrödinger, after saying this and that, refused, but Born was actually interested, and Hans Bethe and Rudolf Peierls, they wrote that if Born came to India and set up a school, they would be interested in coming. So it was really a golden opportunity to India to get some of the top scientists of that period. So in fact, Max Born did come to India. This is Born as he looked in this. He was very interested in Indian philosophy and such things. So here we have a picture of Max Born at the IISc. You can recognize, those of you who've seen it can recognize the main building. So in the winter of 1935-6, Max Born and his wife Hedwiga or Hedi came to visit IISc Bangalore. So here you see Professor Born, Raman, Mrs. Born, Mrs. Raman, and these are all the other faculty of IISc at that time. So Raman invited him for a one-year visiting professorship, which was all he could give as director of IISc. And here, the Borns, they liked Bangalore so much. So Bangalore was not what it is today. It was a very quiet, very peaceful, very beautiful city. Okay, no pollution, very few cars, and of course no IT industry. But they really liked Bangalore, and they wanted to stay there. And remember that they came from Europe where there were these Nazi marches, concentration camps, glass-breaking night, and all these things were happening. So they were happy to be away from all that madness. So Raman gave, as I told you, gave Born a one-year visiting professorship. And Born found a young collaborator in Raman's student, Nagendranath. So this is a picture of Nagendranath, with whom he wrote a paper in the Proceedings of the Indian Academy of Sciences. As I said, it came out from Bangalore. And it was called the neutrino theory of light. So then it was fashioned. Remember, there were only two massless particles. The neutrino was massless. Well, it was massless in those days. And then the photon is massless. So the idea was that perhaps the photon is a composite of a neutrino-antineutrino pair. There are two spin half particles which come together to give a spin 1 particle, which is possible, right? Two spin halves can come together to give you spin 0 or spin 1. And therefore, the idea, of course, this is wrong because neutrinos don't combine like that. But the idea survives because quarks can combine like that. And later, the same idea comes with the quark. And the rho meson is a composite of a quark-anti-quark pair. So in a sense, the idea survives. Many ideas today have roots very far back. Okay, now Raman tried to get Born a regular position at IISc as a professor of theoretical physics, but this ended in a disaster. So in the IIT faculty, which consisted only of the IIT professors, an Englishman called William Aston, who was an electrical engineer who knew nothing about theoretical physics, he stood up and said that the IISc cannot create a chair for a second-rate foreigner who couldn't find a job in his own country. And we are IISc, we cannot offer a job to anybody and everybody. So the IISc refused to give a permanent position to Max Born. Later, Raman appealed against this decision to something called the IIT Review Committee, which was the equivalent of their council. And they said that, why is Raman trying to employ a mathematician whose work has no relevance to industrial research? The IISc should do industrial research, and Born's work has no relevance to that. And the IIT Review Committee included Meghnad Saha. So that is a sad episode in the history of Indian science. So Max Born in his life says that after the meeting, I went home to Hedi and cried, but actually it is Indians who should have cried and who should be crying still. Okay, let's talk about more pleasant things. In the 30s, of course, there was a lot of disturbances and turbulence in Europe. Still, of course, great science was being done. But in India, it didn't reach India, so people were happily pursuing theoretical ideas in India. Meghnad Saha at that time was working, apart from throwing out Born, he was working on his theory of monopoles. So he tried out a theory in which he could think of the newly discovered neutron. It's somewhat similar to the Born-Nagendranath idea. The neutron could perhaps be a bound state of two monopoles of opposite, of opposite charge, but magnetic charge. So essentially things like dyons. This would explain why the neutron is neutral but has a magnetic dipole moment. So it's just a dipole, magnetic dipole that way. Now this theory did not last, but of course we know that Saha's derivation of the monopole directly from Maxwell's equations is perhaps more mathematically elegant than the Dirac definition, which requires this long string. And of course, perhaps Dirac's thing is more intuitive, but Saha's is sort of mathematically neater. But anyway, this theory didn't stand. But of course, we now know that the magnetic moment is due to the neutron having electrically charged components. So you just see that. There was a gentleman called Kulesh Chandrakar in Presidency College, and with his collaborators, he developed a theory of the atomic nucleus. So the idea here was that the nucleus, so already people were beginning to see repetitions in nuclear spectroscopy, which today we know as the shell structure. So the idea was, again, this idea had been proposed by Rutherford. He wanted to repeat his triumph with the atom. So he thought the nucleus perhaps has a negative core surrounded by protons. So a negative version of the atom in a small set. And of course, in some sense, so what these people tried to do, they tried to apply the Schrodinger equation to that and try to get the energy levels. In a sense, this is similar. The mathematics is similar to what you would do in the nuclear shell model, which came much later. Of course, after that, Kerr went into doing something else. He was one of the first people who started criticizing Einstein's relativity, but he had scientific reasons, not racial reasons. And today, if you look at, there are websites which talk about quote-unquote alternative science, which are mostly based on misunderstandings of correct science. But his books are very, very highly regarded in those circles. But it's a bit sad because he was actually doing what was frontline research in those days. Okay. Now, since this is TIFR, I have to talk about Homi Bhabha. And this is the Homi Bhabha auditorium, of course. So, in a sense, Bhabha's work was the most impactful of all of these. So, Homi Bhabha, so there are some people here and it's also going outside. TIFR people don't need to be told that Homi Bhabha was a young Parsi boy from a wealthy family closely related to the Tatars. And he was sent to Cambridge to study engineering. But at Cambridge, he came in contact with people like Thomson, Wilson, and Dirac, particularly Dirac, and he determined that he would become a physicist. Okay, so if you go outside here, there is an exhibition. This is for the outsiders. There is an exhibition on the life of Bhabha, so I suggest you take a look at it before you leave. And it tells you exactly how he went through this and what are the very poignant letters he wrote to his parents demanding that he should be allowed to do physics. So he was a protege of Dirac, and he spent a total of 9 years in Cambridge and worked among others with Fowler, who was his PhD supervisor, Dirac, Pauli, Bohr, Fermi, and of course with Heitler, which I will tell you about. So his 1936 paper called Scattering of Positrons by Electrons with Exchange on Dirac's Theory of the Positron was the first calculation of what is now known as Bhabha scattering. And it was one of the foundational works in the newly developing subject of QED, or quantum electrodynamics. And of course, remember, this was long before the days of Feynman diagrams, so everything had to be done from first principles. But you may ask, okay, he calculated one process. Why was it important and why did it get so much recognition in those days? So I'll try to explain that. So Dirac had written a 1928 paper on the relativistic theory of the electron, and that included negative energy states. So you can read about this in textbooks. But the essential problem is that if you have negative energy states, identical electrons can keep getting exchanged between positive and negative energies J's, and that would result in the velocity keep getting reversed. So the electron, instead of having a smooth path, keeps doing a path like this, and this is known as Zitterbewegung. So to prevent this obviously crazy thing, one requires to forbid this type of exchange, and this led directly to Dirac's idea that there is an infinite sea of filled electrons, which is called the Hole theory. Now, of course, in 1930, of course, people did not believe this. Most people did not believe this Hole theory. But in 1932, Anderson discovered the positron, which was a hole. So it is the first so-called antiparticle. And so in 1933, Pauli and Weisskopf set them up to invent quantum field theory, which is theory of both particles and antiparticles. And now, if this theory, this quantum field theory idea is correct, the question arose, is the positron really the antiparticle electron? Or is it just a different particle which happens to have the same mass but positive charge? Remember, the proton and neutron are not antiparticles of each other, but they have almost the same mass. Could this be also true for the positron? How could you tell? So Bhabha set himself to the task of calculating the cross-section for electron-positron scattering under these two assumptions. One, that the positron is the antiparticle of the proton, of the electron, and one, that the positron is a separate particle altogether. Now, I'll show you this in terms of Feynman diagrams. It's easy to understand it. So if the positron is a different particle, then it will scatter from the electron in this way by exchanging a photon here. So here's the positron, and here's the electron. They exchange a photon, and the positron is scattered. So if you do this, your scattering diagram will show a differential cross-section which goes by this formula. This is the Rutherford factor, and then 1 plus cos to the 4 theta by 2, where theta is the scattering angle, the angle between the initial electron and the final positron. However, if the positron is the antiparticle of the electron, you can have another diagram, where the electron and positron annihilate each other to give you a photon, and the photon again creates an electron pair. So this annihilation diagram is possible only if the electron and positron are antiparticles of each other. And if you include this, then you get some more terms here. You get a dependence which is not on this, but also there's a cos squared theta dependence. So now if you look at the angular distribution of the electron or positron in the scattering, that will tell you which of the things is correct. And here is this graph is from much later, but still it shows you the result. So here is this is a histogram of the actual data, and here you see the graph fitted by the annihilation diagram idea. So this is what would happen from its proper Bhabha scattering, and you see it's almost a perfect fit. Now if we had not gone with this, if we had used this formula, then your curve would have been more like this. So in a sense, and Bhabha, there was enough data in Bhabha's time to prove that actually the Bhabha scattering idea with the annihilation diagram was correct. So Bhabha's work proved that the positron is an antiparticle, and therefore quantum field theory is the right way to look at fundamental particles. So that's what gave it this great importance. Within a year, it's amazing that a person can do two very fundamental things of this kind within a year. Of course, we have other famous examples. But in this year, Bhabha started working with Heitler. So Heitler was already famous with Bhabha met him in 1935. In Zurich, he had developed the theory of the chemical bond, which is known as the Heitler-London theory. And he also had been dismissed from his job in Göttingen in 1933. And he sought asylum in England, and he got a position at the Wills Laboratory at Bristol. So they were both interested in the same problem. How do high energy electrons in cosmic rays, how can they come through 8 or 10 kilometers of the atmosphere and reach the sea level? So everyone, by then it was understood that cosmic rays are essentially high energy protons hitting the outer atmosphere, which then cause other reactions. There are electrons produced there, and these electrons come all the way down to the sea level, and we detect them. Okay. So they were interested in the same problem. Now why was it a problem? It was a problem because Hans Bethe and Heitler had already calculated the energy loss which a high energy electron would make in the field of multiple nuclei of nitrogen or oxygen. So what is multiple nuclei of nitrogen and oxygen means air. So what would happen to them in air? They concluded that there was no way such electrons could penetrate more than about 2 kilometers. After 2 kilometers, you would hardly see such electrons. But you can see, if you put a detector on the ground, you will see lots of electrons. So where are they coming from? How are they coming through this 8 or 10 kilometers if they can't go more than 2 kilometers? So this is the idea they were worried about. Okay, I've just said this. So now the idea that cosmic rays could produce cascades like an avalanche. You know what happens in an avalanche? A little piece of something slips, then more snow moves. That snow pushes more snow and more snow, and eventually the entire hillside comes down in an avalanche. So the idea of an avalanche, that's the kind of thing could happen, was in the air. Okay, Bhabha had heard it from Hugh Carmichael, who was at Cambridge, and Heitler had heard it from Lothar Nordheim, who was at Munich. But these seniors didn't take this cascade idea too seriously because they didn't believe in quantum electrodynamics. It was a very new idea, and they thought that there must be some mistake in the Bethe-Heitler. They didn't bother to really work out the Bethe-Heitler theory. They thought there is something wrong in Bethe-Heitler. So they didn't worry too much about it, but they had told these people. But these younger people, and of course Heitler took his own work very seriously. He could hardly say Bethe-Heitler was wrong. So they took it up seriously, and they came up with this beautiful paper, which is called The Passage of Fast Electrons and the Theory of Cosmic Showers. Bhabha and Heitler, Bhabha from Cambridge and Heitler from Bristol. And of course their idea is what is now in the textbooks, that an initial cosmic comes, creates a long big shower of lots of different particles. And what you see as electrons at the ground level are not the ones which are being produced up there, but they are the ones being produced down here within 2 kilometers. So that explained this problem. So the Bhabha-Heitler theory was published in 1936 in the Proceedings of the Royal Society. No World Wide Web in those days. So a year later, in 1937, Carlson and Oppenheimer published the same results in the Physical Review, but they were too late. It's known as the Bhabha-Heitler theory, and not the Carlson-Oppenheimer theory. So they missed the bus in that sense. All right. Now, Bhabha's remaining years in Cambridge, I call the Midas years. You must know of the story of King Midas. Whatever he touched turned into gold. So at this time, it was like that with Bhabha. Whatever he worked on produced excellent results. So in 1936, so the cosmic rays in those days were found that there's something called a hard component, which seems to be coming from the top of the atmosphere, which is not absorbed like electrons. And it seemed to be a new particle similar to the electron, but about 100 times more massive. Of course, we know today it's the muon. And in 1937, Anderson and Neddermeyer had discovered the muon, which is like the electron, but which is 200 times more massive. So, but it was Bhabha who had first suggested that this hard component you are seeing is due to a new particle. It's not any of the particles, you know, it's not a high energy electron, it's a new particle. So that idea first came from Bhabha, which is not so well known. In 1935, Yukawa predicted the pion. Why? He said there's a spin 0 particle mediating interactions between spin half nucleons. So if you want to write the interaction, spin half plus spin half, as I said, combines to give you spin 0 or spin 1. So the spin 0 had been used by Yukawa. So Bhabha pointed out that if there is spin 0, there had better be spin 1 also. So he predicted the rho meson. And this was in 1937. The actual rho mesons were discovered only in 1961, showing you that Bhabha had made this prediction way ahead of time. Then came perhaps the most commonly used result. So muons were seen to be decaying within about 2 microseconds. Multiply that by the speed of light, and you will only get a small distance. How are muons coming from the top of the atmosphere down? So Bhabha proved that that is not due to cause showers, but that is because of time dilation. Now remember that Einstein's theory of relativity, this was during just before the Second World War had started. So there was a huge attack on Einstein's ideas. People started calling it Jewish metaphysics, wrong ideas, it's all sorts of things. But Einstein, here was Bhabha showing that, look, here is relativity which gives you exactly the right time dilation and which shows that this is come. Now today, everyone does this as an exercise, right? It's given to you as an assignment or an exercise. Perhaps you are asked to do it during an interview. So explain it. But this was first shown by Homi Bhabha in the days when a lot of people didn't even believe in relativity. Okay, so these Midas years then passed, and as you see, that Bhabha was very highly regarded by his contemporaries. You see him here with some very famous scientists, and it does look like Bhabha is doing all the talking. But of course, this is from a film. All right. Now, so if Cambridge was Bhabha's Eden, his paradise, well, like humans were thrown out of paradise, Bhabha had to leave Cambridge, and the particular snake in this case happened to be this gentleman you see here. So in summer of 1939, he came home from Cambridge. He had not come home for 6 years, so he came for a vacation with his family. And before he could return, the Second World War broke out, and all civilian passengers were banned from going on ships. Why is that? Because the Germans had sent these U-boats, which were actually submarines, and therefore civilian lives were at risk. Only military ships could come and go. So Bhabha was stuck in India. He could not go until this ban was lifted. So now he was forced to seek a job in India, and of course there was no lack of takers. So for a while, so Kothari tried to lure him back to Allahabad, and Raman tried to take him back to Bangalore. So Raman made him many, many promises. Some of those letters are in our archives here. And he promised him that he would give him all the facilities he needed to start a cosmic ray group in IISc Bangalore. So Bhabha was taken in by all these promises. He went to IISc, and Raman gave him a couple of empty rooms and said, here, set up your cosmic ray group. So young researchers, young experimentalists will be very familiar with this phenomenon, I guess. So anyway, but Bhabha did, for the first time in his life, Homi Bhabha faced the reality of doing science in a colonized country. He'd been born with a silver spoon in his mouth, went to the best institutions, went to Cambridge, participated in the very vibrant scientific atmosphere there. But for the first time, he came and started seeing the reality of doing that. And remember, in India, there was hardly anything. To give him credit, Bhabha worked very hard during this period. For 6 years, he worked very hard in Bangalore. He both tried to set up an experimental cosmic ray unit, and at the same time, he did some of his theoretical ideas. But I think it is also fair to say that none of this theoretical work has the impact of his Cambridge work. Perhaps it was because he was away from the environment, perhaps it was because he was trying to pursue all the ideas which he had not pursued in Cambridge. Whatever be the reason, he did excellent work there, but none of it has that impact and that originality. So here is a picture of two things. Here is Bhabha trying to launch a balloon to measure cosmic rays from ISC. And here is a picture of a paper written by Bhabha and Corbin. So they set up this classical theory of spinning particles. So generalization of Dirac's equation known as the Bhabha-Corbin equations. So he was working, had lots of students, was active, but against all the odds which he faced. Now, the difficulties he faced, especially the experimental part, convinced him that he needed to build institutions. And so at that point, he became an institution builder. So the TIFR was founded in 1945. It started from this bungalow, Kenilworth, on Pedder Road. Of course, the bungalow doesn't exist anymore, but it was his aunt's bungalow. It started from there, and this is where it is today. And then in 1954, he was asked to set up the Atomic Energy Commission, and then he did a lot of work setting up BRC, setting up atomic reactors, and so on. So after that, his interest shifted more to institution building, where he did a great job, of course. That's why I'm here, that's why you're all here. But moved a little away from doing the basics of science. Okay, so let me now move to the other end of the country, to Sandakphu, which is near Darjeeling. And now let me tell you that charged particles leave tracks in photographic emulsion. That was well known, and the first person to point it out was a Japanese scientist in Cambridge called Kinoshita. So typically you get tracks like this from charged particles on photographic emulsion, which is really silver bromide or silver iodide. So the effect of these charged particles is to precipitate silver out of these. So you get these streaks of silver, and then if you fix it with some material, you get silver oxide, which is or silver sulfide, which is black, and then it just shows up against the light. Now, the first people to think that you could use this for cosmic rays were two ladies from the Radium Institute in Vienna. The leading person was Marietta Blau, and whose picture is on the poster, and Hertha Wambacher was her student. So now these two ladies were the real pioneers in this work, but I have to tell you with some sadness that this work, I think it was of Nobel-worthy quality, but both these women were victims of severe gender and political discrimination all their lives. I'll tell you a little more about it as we go ahead, which is probably why most people have not heard their names at all. So the 25th session of the Indian Science Congress, so Indian Science Congress was smaller in those days than it is now, and perhaps more intense and more serious than it is now. It was held at Kolkata in 1938, attended by various luminaries from around the world, including, and it was supposed to be addressed by Rutherford. Of course, Rutherford passed away just before this, and his speech was read out by Meghnad Saha at the meeting. They didn't have a new president, but they read out Rutherford's speech. So now there was a cosmic ray session, and there two very famous people had come. There was Geoffrey Ingram Taylor from Cambridge, who was sort of the leader of the cosmic ray work there. And there was Walter Bothe, you know his name. He later got the Nobel Prize for the coincidence experiments, method in experiments. So they discussed a lot of cosmic ray techniques. And Bothe in particular, he discovered this new emulsion technique, which Blau and Wambacher had studied, and said, this is a new technique to do cosmic ray work. And so it was discussed. Now, of course, many discussions happen. It's not always that people, at conferences, it's not always that people pick up from the discussion. But in this case, there were two people who picked it up. So D.M. Bose, always interested in cosmic rays, he was 53 years old then, and he had just become director of the Bose Institute, succeeding his famous uncle. And he had a student called Bibha Chaudhary, and they decided to try out this new technique. So now, of course, they didn't have balloons. So they trekked to Tiger Hill and to Sandakphu, both near Darjeeling, at heights of 8,500 feet and 11,900 to expose photographic plates to cosmic rays. Now, this is easier said than it is done. Here is a Google map. So if this is Darjeeling here, you have to go to Tiger Hill here, and Sandakphu is there. And either you trek there, take the long trek there, or you go on muleback or horseback if you can ride horses. It's not easy. There were no roads. Nowadays you can go to both places by road, but in those days you could not. The entire distance you had to go on that, and they had to go once a month. So actually put in real serious physical work to do that. So what did they do? So what they did was the following. Sorry. So in those days, photographic plates were really plates. They were not rolls of celluloid, but they were glass plates coated on one side with this silver halide. So they came plates like this. Ilford was a famous company, and they came as a dozen plates at a time. And this is actually how they looked. Here's a box, and you had these glass plates with coating. So they used to take these plates, take a stack of these plates, and expose them to cosmic rays. By the way, what you did with those plates was you had things called a box camera. Some older people in this audience have seen it, I guess. You opened the front of this, you pushed the plate in right to the back, closed it, covered everything with a cloth, and took an exposure. And then you took out the plate and washed it. And it is with this technique that such iconic pictures of the Second World War and so on were taken. So they did this exposure, and soon they were able to use it to start detecting. So mesons were the new thing in those days. So they were called mesotrons. Yukawa had called them mesotrons. So here is the first paper, again from Nature. You see Nature up there. So I'll expand this for you. So here's this paper, photographic plates as detectors of mesotron showers. And he says, in the last 2 years, we have been using this and so on. And this is signed D. M. Bose, B.Y. Chaudhary. It's a detailed account of the transaction of the Bose Institute. So he was promoting his own journal, but it is from the Bose Institute. And it's a bit fuzzy, but you can see the references to Blau and Wambacher, Bothe, other famous names, Wenzel, Heisenberg, and so on. So there are also people who have worked on this. Now, there was a rumor, which I had heard, that they had actually discovered the pion. That they had actually discovered the pion before it was formally discovered. So let's investigate this question. So the first thing I need to tell you is that during the war, they had access only to what are called half-tone plates coated on one side. All the plates which were full tone, which were coated on both sides, were reserved for war work, for air reconnaissance work. And they were not available even to English civilians, they were only reserved for the military. And of course, quote unquote natives would not even be allowed to touch them. So they had to work with half-tone plates. And half-tone plates give you very grainy pictures. Can someone recognize that building in the picture? It's Howrah Station, as it used to be then, and this is a modern picture. So you see the difference, how grainy the picture was. So remember, the physics was also being done at this level of resolution. So they found mesotron. So they found the length of the track. From there, they calculated the mass. And here are so this is the actual mass of the muon, as we know it now. Actual mass of the pion, muon is about 105 MeV, pion is about 140 MeV. And here are the, so I've just blown up this last column here and converted it to MeV. This m naught is the mass of the electron. So you see what they had found. They had one data point which is close to the pion. Others are closer to the muon or even less, and they have a huge error. Okay, the error is about 25%. So it's difficult to conclude from here. It's likely that most of what they saw were muons. Maybe there was a pion which they also saw, but they certainly did not understand that there's a difference between the two. At that time, nobody did. So we can't blame them, but they certainly were the first people to try to measure these masses of the mesons and to use this technique. So they were certainly pioneers in this respect. Okay, let me tell you about the real discovery of the pion. That happened after the Second World War, and partly because of it. So these four people, Powell, Occhialini, Merhead, and Lattes. So Blackett, who had been involved in a lot of war work, he asked the plate manufacturers, now give high density people, because you want high density plates for the Cold War. You want to have planes which will take high resolution pictures of what the Russians are building. So the government sort of told these people, you may do what these people tell you. So Powell, of course, had easy access to this, so he was also involved in the war work. And Lattes was the person who suggested that put more boron in the emulsion for whatever reasons. But this worked like magic. So in the very poetic words of Powell, which he gave during his Nobel lecture, he says it was as if suddenly we had broken into a walled orchard where protected trees had flourished and all kinds of exotic fruits had ripened in great profusion. The exotic fruit, of course, here was the pion. So these are pictures from their actual paper. And if you see here, there are 3 tracks here. Each of them has a track like this, a track like this, along, and then another track like this, a faint track like this. So the way we interpret it is that at the top here is a pion which comes, a neutrino goes out, and a muon goes this way. Similarly here it's like that. All of them have a neutrino going out, and there's the muon. And then at the bottom here, the muon decays. 2 neutrinos go out, which are not visible, and there's an electron. So electron and 2 neutrinos in each case. So this is how we understand it. And this was the first. But see, with the you see this resolution, and you see the long track of the muon. It's very unlikely that with the resolution which Bose and Chaudhary had, or other people had, they could have looked at this little pion track. They would, most unlikely, they would have seen it just as some blur and seen the muon track. So it was definitely the improvement of the emulsion which allowed them to distinguish and say clearly that there are 2 kinds of mesons. However, the idea, theoretical idea, had already been seduced. So Tanikawa and Sakata and Inoue in Japan, they had suggested these ideas. But in 1942 and 1943, this World War was raging. Japanese journals did not go anywhere outside of Japan, so nobody else read it. And then Bethe and Marshak at the Shelter Island Conference in 1947, they made the proposal, but you see the communications were not so fast in those. They did not realize that Powell and company had already made that observation. Okay, so what happened afterwards? So Cecil Powell walked away with a very well-deserved Nobel Prize in 1950. Giuseppe Cialini returned to Italy. He won the Wolf Prize in 1979 for this work. Cesar Lattes went back to Brazil to lead the cosmic ray research there. Hugh Merhart worked on parity violation. He wrote a very famous textbook, which a generation ago was standard reading for any particle physicist. Marietta Blau, she was dismissed from her position by the Nazis, and then she never got a regularly paid position, and eventually she picked up cancer from her studies with radiation, and she died in 1970. The worst to fare was Herta Wambacher. Not that she was perfect. So during the war, she turned into a Nazi. She tried to take all the credit for their common work. And then after the war, she was imprisoned and taken away to Russia by the Russians. And when they realized that she had cancer and was dying from that exposure to radiation, then they let her come back. So she came back to Vienna and died in 1950. So that's what happened to these people. But you will find all these in the literature on cosmic rays and other pion discovery. But for Bose and Chaudhary, there is never anything. So I will change this statement to say that it is famous quote by Tennyson, it is better to have tried and lost than never to have tried at all. So I would be very happy to tell you that the Nobel Prize went to Powell, Blau, and D.M. Bose for their pioneering work, but it didn't turn out like that. Okay, come back to Bombay. Don't think Bombay was left behind in those days, okay? So this is the Wilson College as it used to look then. Much of it looks similar now. But in Wilson College, there were 2 gentlemen who were doing the same kind of work. And here is their paper from there. H.J. Taylor, who was actually Rutherford's student, and Vishnu Dabholkar from Wilson College in 1935, they were doing the same thing. Alpha particle tracks at Ilford and so on. But they were not looking for mesons, they were looking for alpha particles. So they missed the great work at that stage, but they were also doing this. I learned that Taylor also did some very fundamental work in statistical mechanics, which I don't really know about, but he also did some fundamental work there. It was being done from Wilson College, and it's rare that you see fundamental work of this kind coming from an undergraduate college today. Okay, now I come to Vikram Sarabhai. So, why are people laughing? Oh, sorry, I have the wrong picture. Okay, sorry. So perhaps Vikram Sarabhai could have had a different career also if he wanted to. But so he also came from a very rich house, and he had a passion for science. He completed his mathematical tripos But he had, perhaps things had relaxed since then, or he had more courage. So he risked his life on the sea voyage and came back to India. And Raman, who had this jeweler's eye for bright people, he immediately offered him see, this guy was just past his some kind of bachelor's degree, and Raman immediately offered him an assistantship at the ISC. Now, he was only 21 years old at that time, and there was Bhabha, who was 10 years older than him. And at that time, Bhabha was already in ISC. He was already a famous name for Bhabha scattering, for Bhabha-Heitler theory, and there were lots of students around him. But Sarabhai did not attach himself to Bhabha. He decided that he would work on his own, and he had the courage and confidence to do that even at the early age of 21. So his interest was not quite in the Bhabha's interest. He was interested in the effects of the Earth's magnetic field on the cosmic rays. So during the 6 years of the World War, for 40 to 45, he published 6 single author papers, all in these famous journals. So here is one for mesons, again interested in mesons. Here is another one, and there are 6 of these, all single author papers from there. And then after the war, he went to back to Cambridge. He collected these together, wrote a thesis, and got his PhD from Cambridge, Cosmic Ray Investigations in Tropical Latitudes. From Cambridge, Sarabhai came back to India. And again, like Bhabha, it helps to have relatives who are very rich. So again, like Bhabha, he had money from his own family, money from his family friends. He collected that and started a new institute, which of course is the PRL today. And he was only 28 years old when he founded this. But unlike Bhabha, who became the director of his own institute, Sarabhai preferred to remain a simple professor at his institute. He roped in K.R. Ramanathan, who was Raman's student and who had retired from the Indian Meteorological Department, to be the first director. So to do all the administrative work while Sarabhai could concentrate on the science. So only when Sarabhai Ramanathan retired in 65, Sarabhai took over as director. But you can imagine that he must have had a big say in things. So during this period, he trained 19 PhD students, among whom was the last surviving was the late U.R. Rao, who had been chairman of the thing. So here's a picture of U.R. Rao as a young man, and of course, as you know, I think he died a few months back. So Sarabhai was a very simple person, and he worked immensely hard. He worked so hard that he died at 52, and people say he died of sheer overwork. Okay. Now, what happened? Sarabhai's interests. So first he was interested in cosmic rays. As you see, he was interested in the effect of the Earth's magnetic field on cosmic rays. So then it changed to planetary magnetic fields. From planetary magnetic fields to solar physics, the connection is clear. From solar physics to satellite-based observations. And if you want satellite-based observations, you need to launch satellites. So that is how he came to found ISRO. And here you see him as the founder of the India Space Program. There's another famous person in this picture. Can anyone recognize him? This one. This is Abdul Kalam, yes. Well, his hair was short in those days. All right. So finally, today, when you see a PSLV launched, you must remember this is because Sarabhai was interested in cosmic rays. All right. So let me talk about the cosmic ray group at TIFR, come back to TIFR. So Homi Bhabha was the leader of the group, of course, but then he was mostly involved in setting up BRC and the DAE, not so interested. I think he would come here only on Wednesdays. The main person was Bernard Peters. So Bernard Peters had an interesting career. He was born in Poland. His real name was Bernhard Petrowski. And his parents had escaped from Poland to escape from the Russians. Then Peters grew up in Germany. And then because he was Jewish, he had to escape from Germany to the US to escape from the Nazis. During the US, he worked on the Manhattan, the atomic bomb project, and so on. He was a well-known scientist. But he was also a communist by conviction. So after the war, when the anti-communist hysteria, the McCarthy years, started in the US, he had to escape from the US, and he came to India. And he stayed 8 years in TIFR, after which he left TIFR and went to Denmark, where he spent the rest of his life. We don't know why he left India, but I hope it was not to escape from Homi Bhabha. But let us see. So he was the real leader of this group. And then came M.G.K. Menon, later director of this institute, who was a student of Powell and who had joined TFR in 1955. Other people who had done their PhDs here were Srikantan, who was Bhabha's student. There was Devendra Lal, student of Bernard Peters, and there was Yashpal, who later did his PhD with Rossi at MIT, and of course we know he's famous. And of course, to most people, Yashpal, this face of Yashpal is not famous. The one which is more familiar is the Yashpal of Turning Point, those who have seen it many years ago, of course, even that is many years ago. Okay, and here is a list of the first few theses done from here. The first thesis was by R.P. Thatte. We have that in the library here. And of course, in the beginning, Homi Bhabha was the only recognized guide, so everyone was Bhabha's student. Later, you see others coming in, Peters, Dosar, M.G. Kemenan, Dharmatti, and so on. And among the PhD students, Srikantan, Devendra Lal, Vijay Raghavan, P.V.S. Rao. So names familiar, very familiar to TFR. So the 50s were a fabulous period for particle physics in many ways. Lots of new and exciting things happened. So here are some of the list of the particles discovered in the 50s, and here are some of the new ideas which came. Yang-Mills theory came in 1954. The intermediate vector hypothesis of Schwinger came in 1957. Parity violation 1956. The V-A theory was after 1958. Exciting things were happening. Even an early version of the renormalization group had been suggested by Stuckelberg in 1953. So lots of exciting theoretical developments were taking place. And a host of new particles were being discovered, and many of them just won the Nobel Prize for discovering the new particle. However, I have to say that the TIFR group in particular and Indian cosmic ray research in general was nowhere involved in all these momentous developments. It is sad to say this, but what had happened was something a little unfortunate. Bernard Peters, he had diverted much of the work to production of exotic nuclei, what we call transuranics today, in cosmic ray collisions. Well, that's one way you can do it. But it's a research dead end because high energy reactors do it much better. And that's what people have done since. So much of the work which could have led to the discovery of all these famous these particles was instead diverted to looking for heavy nuclei, which is at the other end. And TIFR did not have another theorist in those days of Bhabha's caliber, and he himself was too busy. Bose and Saha were then past 60, and Kothari, the other person you've seen, was too busy as the advisor for the defense ministry. So there was no one really to take up the cudgels in the 1950s and do real path-breaking science in the sense which had been done in the 40s and 30s. However, there was one thing which happened which was really state-of-the-art, and that was the set of experiments in the Kolar goldfields. So let me talk about the Kolar experiment. So if you want to go to Kolar, so you take the road from Bangalore through Hoskote to somewhere here, and there's a town called Robertson Pet, which you come together. And from there, the Kolar goldfields are very close. So you go there. So Kolar is here. And then you have to go by cart through these narrow roads to Sanpet. And here, so there existed many mines, gold mines, and that included the Champion Reefs mine, which had been set up, as you see, in AD 1900. And here is the Champion Reefs mine building. So this mine shaft goes down some several kilometers into the earth, and as early as, so it goes down, you see, it can go as far as 7.3 kilometers. But as early as 1948, Bhabha sends his student Srikantan to Kolar. He said, go down the Champion Reefs mine and measure the cosmic ray flux at depths of 10,000 feet or more. And with Srikantan, two other people who helped him were Naranan and Ramanamurthy. And they also spent their entire careers here at TFR. And here you see how the flux goes down. So this is so here, if you look at the water equivalent, this 10,000 feet or more would be somewhere here. So it's not on this curve. Anyway, Kolar is not there anymore. But you see the flux falls. This is a logarithmic plot, so you can see the flux falls very fast. So once you go to great depths, the cosmic ray flux should fall off, and roughly on this exponential looking curve. So in fact, initially they did find that the flux declined, but then they unexpectedly began to rise. Now, Bhabha immediately guessed that this was due to some radioactivity in the rocks. It was nothing to do with the cosmic rays. And in fact, some thorium-250 does exist in Kolar at around 2 kilometers, but when you go deeper, this disappears. So it is really an effect of that thorium in the rocks. I should also mention that I read this and heard this talk by Srikantan, that equipment was very difficult to get in those days. But this was just after the Second World War, so a lot of military surplus radio equipment was to be found in the Chor Bazaar. So they used to go to the Chor Bazaar, talk to the smugglers, and buy some equipment from there, and that was what they used to set up the Kolar experiment. So around a depth of 2.7 kilometers, you don't see cosmic ray muons anymore. So this means that if you do see muons there, okay, then that must be due to something else. So you don't expect to see anything. You put a detector, it should be completely silent. In 1955, the neutrinos were discovered. In 1957, Markov realized that neutrinos, of course, could easily penetrate to such depths. And a neutrino can produce a muon by doing an inverse Compton scattering. And therefore, if you do see muons at that depth, those muons must come from neutrinos. So if you see a muon at that depth, so very good, put your detector and see if you can find a muon. If you can find a muon, then there must be neutrinos. So this is the famous experiment. TIFR group took up this suggestion, and one of the people who were then involved as a young student, not as he looks here, was V.S. Narasimhan. He's familiar to many people in this audience. So they took up this work, and here in 1965, they were able to write the first paper, Achar, Menon, Narasimhan, Ramanamurthy, and Srikantan, with their collaborators from Osaka and from Durham. And they were narrowly able to beat the other group, which was led by Frederick Reines, the person who won the Nobel Prize for discovering the nucleus, and his collaborators. And it was narrow, 12th July, 26th July. So they won this race. So we can say that atmospheric neutrinos were discovered in the Kolar experiment, and that was certainly one leading piece of work which was done in India in the 1960s, but the work started in 1950s. Well, what about the Kolar experiment? In the 1970s, the Kolar experiment was revamped to look for proton decay, but as you know, so long as the experiment ran, no events were found. But from 1975 onwards, some weakly interacting particles of a few GeV seem to have passed through the Kolar detectors. So now one wonders, could they have been the first detection of dark matter? If we do find dark matter someday, perhaps we will go back and say it were found there. But the Kolar experiment terminated in 1992. The goldfields themselves were shut down in 2001, and this is how they look today. So it's a picture of abandonment and desolation. Okay, let me now move to the other end of the country. So what was happening in North India during this period? So in North India, so Meghnad Saha's group flourished in the 1930s. Then Meghnad Saha went back to Kolkata, and this group collapsed because most people moved with him. Only A.C. Banerjee was left. All the students went with him, and they went to Kolkata to the Indian Association for the Cultivation of Science. Then D.S. Kothari returned in 1939 to found the physics department at Delhi University. Soon he was joined by Saha's student R.C. Majumdar, and they together built the physics department at DU. I'll come to that. But for the moment, in parallel, P.S. Gill built a cosmic ray group at Aligarh Muslim University. So let me tell you a little about P.S. Gill, because he's one of the most interesting characters I found during the reading up for this thing. So he had a long and eventful life. He was born in a farming family in the Hoshiarpur district in West Punjab, and he had to walk 5 kilometers to school every day. After passing school, he got a job on a ship as a ship hand, and he went to the New World. Then he started as a taxi driver in Panama City. Okay. So today, of course, people go to Panama for other reasons, but in those days, he just went to get a job. And from there, okay, there was no wall separating that part of America from the rest. So he was in the University of South Carolina, and he did his BS there, bachelor's. Now, he must have done very well in his bachelor's, for after that we find him at Chicago. In 1936, he was in Chicago, and he became the PhD student of Arthur Compton. Of course, you all heard of Compton scattering. And he worked on the physics of cosmic rays. Now, Compton and Gill established today what is one of the standard effects of cosmic ray physics, which is called the latitude effect. And it proves that cosmic rays, primaries, do come from the solar wind. And in 1939, Gill again showed that the pion has spin 0. Today we take it for granted. I've been saying it so many times during this talk. But the first experimental proof came from Gill. He got his PhD in 1940. Now, with this kind of work, of course, Gill could have got a job in the US, but he preferred to come back to India. He became a lecturer at the Forman Christian College in Lahore. And there, what did he start working on? Cosmic ray studies at high altitudes. So first he would travel to Kashmir, to Gulmarg, to expose plates. And then when the Second World War was almost over, there were lots of British warplanes stationed around Jaipur. So he persuaded the pilots, when you go up on a flight, please take my plates with you. So they would be exposed on those plates. In 1946, he went on a lecture tour of US and Europe, where he met Homi Bhabha. He didn't meet Homi Bhabha in India, but he met him in Europe. And Bhabha persuaded him to come back to TIFR in 1947. However, for whatever reason, Gill didn't stay here long. Within a year, he was back in the US. And from there, this time, he was lured back to join Aligarh by its very famous Vice Chancellor, Dr. Zakir Hussain, who later became President of India. And then at Aligarh, he built his own cosmic ray group, and his interests were more similar to those of Sarabhai: geomagnetism, shower profiling, nuclear reactions, not the fundamental kind of things which Bhabha was interested in, but a different kind of stuff. So so this is the picture of the Aligarh University Department of Physics. And then Gill, in 1963, he left that, and he built the Central Scientific Instruments Organization in Chandigarh. He retired in 1971, and still energetic. He set up a business in Delhi manufacturing magnetic heads for tape recorders. Okay. And eventually he grew too old to even run that, so he sold his business and went to live with his daughter in the US. I think he died well to his 90s, but by then he had written a book of memoirs in which he has actually blasted every single Indian scientist from the beginning to his own times. Okay. So, all right. Now, Delhi University. So, Delhi University had been set up by this gentleman, Sir Maurice Dwyer. He was the first Vice Chancellor, and this is at a picture of him at Oxford, where he developed his interest in India, and you see him with a couple of other very famous Indians. This was just after Tagore had given his, what lectures are there? The famous lectures on the crisis in civilization at Oxford. And they built up this department, which must be familiar to many people. And there, Kothari and Majumdar, they formed a complementary pair. So Kothari did all the government work, which means he also got all the grants and so on. And Majumdar basically ran the physics department. So they had a good understanding among themselves. So they ran the department and built it up very nicely. So as early as 1942, Majumdar published a paper on electron-meson interactions with a very promising young MSc student called Suraj Gupta. So Gupta later, he's still alive. This is a picture of him a few years back. It's on his website. But of course, Gupta is famous for the Gupta-Bloiler quantization. This is a page from the well-known book by Iziksen and Zubair. And you see, you talk about, it makes a chapter in this. Of course, this was not the work with Majumdar, but sort of these people were trained and inspired by this group. Similarly, there was another student of Delhi University called Jogesh Pati, who in 1974 wrote the first grand unified theory with Abdul Salam. That's the picture. And of course, that is what predicted proton decay. So again, a product of Delhi University and a product of this Kothari Majumdar and their group. Two other very famous people. There was S.N. Biswas, and who in fact is the only Indian to have discovered an elementary particle, co-discovered the lambda particle. He had come to TIFR for a short period, but after 5 years he went away to Delhi University, and then he shifted away from experiment and worked on theory. And two generations of students grew up under his tutelage, and he was generally known to people as Dada Biswas. Of course, he has passed away now. A.N. Mitra, who is still alive, he did his PhD with Majumdar and then again with Hans Bethe, and he worked on this Bethe ansatz, I think, for the most of his life. So he still comes to the university sometimes, and his specialization has always been in dispersion relations at bound states in quantum field theory. Last part of this story, of this part, Alladi Ramakrishnan. So you see him with Niels Bohr here, and this child here is his son, Krishna Swami Alladi, who is a mathematician today at Florida, Gainesville. And so Alladi Ramakrishnan was already came from a very famous family. His father, Sir Krishnaswamy Alladi, was a member of the Constituent Assembly, and he grew up like that. But he was interested in science, and he came to started working with Homi Bhabha here, and started working on cosmic ray showers. So Alladi was perhaps the first to introduce the stochastic methods in particle physics to understand cosmic ray showers. Nobody before them had done that, and therefore, in some sense, this is the father of all the heavy Monte Carlo simulation work which is done today in particle physics. But I have not seen anywhere that people acknowledge that this Monte Carlo simulations in particle physics were started by Alladi and Homi Bhabha. It's shown to start much later, but this is where it actually started. So after that, Alladi went to Cambridge, as most people, collected his work there, and got his PhD, and came back to Chennai. And he joined the University of Madras, where immediately he fought with his head of department. So because he wanted to have a seminar. And the head of department says, this department is for teaching. We don't want all this seminar business. You do it at home. So Alladi started having the seminar at home. So he called it the Theoretical Physics Seminar at his home. In 1960, this Niels Bohr came to India. He went all around India to various places, and including to Chennai, where Alladi invited him to come and join his homegrown seminar, which Bohr liked very much. So later, when Bohr went to Delhi, and he was interviewed by journalists, and they asked him, so what were you impressed by in India? He said, well, Homi Bhabha has built this nice grand institute in Bombay that I liked very much. And I like this small and very intense group of discussions by Alladi in Madras. So this appeared in the Hindu in those days, and such things impressed politicians in those days. So the Prime Minister, Jawaharlal Nehru, read that article, and then he called up the governor of Madras, whose name was C. Subramaniam. So C. Subramaniam, of course, people don't remember him today, except that he was Reserve Bank governor at some time. So you will find his signature on some old notes. So Subramaniam actually contacted Alladi and said, the Prime Minister is coming to Chennai and he wants to meet you. So Alladi met Nehru, and Nehru said, okay, you have this nice group, how can I help you? So Chennai said, give me money and let me build an institute. So that's how math science started in the year 1962. So that's the start. Okay. Now, before I go ahead, let me just show you a little video. So please watch it while I get myself a drink of water. So that is how science grew in the West. From small beginnings, it proliferated into various branches, various things. It grew over the years. It has grown over the years into a mighty tree with many branches, many people, a lot of resources, and it's a huge thing today. So in India, of course, we have started much later. So we are not at this stage. We are at an earlier stage. Now, of course, you see, a mighty tree like this, you cannot plant it and then say that I will pour a lot of water into it and put a lot of fertilizer and I expect it to grow to this size in a week. It will not. So let us look at the growth of Indian science. I will just show you this by showing you the centers where particle physics and cosmic ray theory is being done in these days. So in the 1970s, there were the following centers. Then these were the new ones set up, or new particle physics centers set up. IIT Kanpur hired some people, so did BHU. T.N. Pradhan founded the Institute of Physics, Bhubaneswar. University of Hyderabad, a few people moved there. Mukunda went to ISC Bangalore. The first DAE High Energy Physics Symposium was held at IIT Bombay in 1972. In the 80s, you didn't have too many new centers. The first SERC Theoretical High Energy Physics School was held at ISC in 1985. The first string theory school was held at IIT Kanpur in 1986. These are when the community started getting together. And the first workshop on high energy physics phenomenology was held at TIFR in 1989. These are things which bound the community together. In the 1990s, only 2 new centers came up, HRI and IIT Guwahati as particle physics. The first experimental SCRC school was held at TFR in 1995. Between 2000 to the present, we have had several new centers. So all of these places have hired particle physicists and are trying to set up particle physics groups. And the hope is, of course, that we will also have the INO. Now, I expect that, let us say in the next 20 years, there are several other centers in the country where I also expect to see high energy groups. So it should grow like this. So this is why I said that, like the tree, we are having more and more leaves and branches being put out, and hopefully that is how things will go. Okay, so I've taken up a lot of your time. So let me finish with a few observations. These are not meant with malice to none. There's just some observations which struck me while I was preparing for this lecture or preparing the material. So the first one is that you will notice the tremendous influence of Cambridge University and the Cavendish Laboratory in building physics in India, particle physics and nuclear physics in India. And here there are some things to be said. First of all, remember, we started from a time when there was no postgraduate education in India. So Cambridge was the place to go to. And you will also see that the closer people were to Cambridge, the more recognition their work got. So Homi Bhabha, who was sitting in Cambridge, his work got the maximum recognition. And as you move away from Cambridge to people who are not connected, if you move away to D.M. Bose and Bibha Chaudhry's work, which was not connected with Cambridge in any way, it hardly got any recognition. Or even though the Taylor and Dabholkar's work was in Bombay, and though Taylor was a Rutherford student, these have been lost on the way. So the importance of Cambridge and the fact that a lot of Indian work was considered as an appendage to the Cambridge group did help. So after independence, that umbilical cord got cut, so we instantly were on our own. The second thing, of course, is that administrative posts or institution building took away many of the great scientists, sometimes in the heyday of their work. You see, Bhabha founded TFR when he was only 36, Sarabhai founded PL at 28, Meghnad Saha 50, SINP, Kothari became the UGC chair at 56. So none of these people, all right in the middle of their scientific careers, of course, they had very good intentions to build science, to help others, but it remains, the big question is that could the people for whom they have built it, have they been able to take up the challenge? The fourth thing I noticed, that you will notice that there are, in India, of course, we put the gods on the same pedestal, male and female, but in India, for particle physics, except for Bibha Chaudhry, it has been more like this. So that, of course, we have to seek the causes in many things, but that's how. So 50% of the brains of the country were not tapped. Anyway, to conclude, the pioneers of science in India, they were fearless, energetic, and confident, as you see. They tackled cutting-edge problems without fear of failure or ridicule. So you see, sometimes they did crazy things. They were often wrong, but this did not deter them from coming up with fresh ideas. And they were willing to tackle the most difficult of problems. You see that D.M. Bose was doing cosmic rays within 2 years after its discovery, and with minimum equipment and sometimes money out of their own pockets, and as I told you, going to the smugglers in Chor Bazaar to buy instruments. They had huge ambitions, and they worked tirelessly to see them fulfilled. So after reading all this, I thought that this is the most important lesson to draw from their story, that to have ambitions and to hope to do more, and I think that is what could be the best thing to learn from this. So thank you for listening with attention.
Thank you, Srirup, for this very comprehensive, very exhaustive kind of history of the entire, spanning over almost 120, 130 years. I know we are quite late at this time. If there is just 1 or 2 questions, maybe we'll take before we disperse for tea, especially from younger audience.
No?
No questions?
Yes.
Yeah. Right. As he asked, I also want to announce the tea today is being served in the Homi Baba cafeteria. Yeah, please.
Because the work he did is not quite particle physics. It's very fundamental to quantum mechanics. So there is very fundamental work in nuclear physics done by Meghnas afterwards. He built the first cyclotron. And there is very fundamental work done by others, which I didn't talk about because I concentrated on particle physics. If I was going to talk about the history of theoretical physics or history of science, then of course Bose would have a huge part to play. But Bose's the work which Bose did was more essentially statistical mechanics of those days, applying quantum mechanics to statistical physics. Yes? All right. Maybe it's going to be put up outside. Thank you. Can you take this? I will. Okay. Sure. One at the back. If you shout, yes. Okay, thank you. So all of particle physics is done using natural units, where you put c, that's the velocity of light, to unity, and h bar, which is the quantum, basic quantum of angular momentum, to 1. So all of particle physics is done in that because it's the most convenient, makes the equations easiest to write. There is nothing fundamental about choosing a set of units. It's just that it's more convenient. And I think people have been doing that since at least the 1950s. So when I teach a course, the first lecture is on natural units.
Okay, so let us thank Srirup once again for this.
Thank you. Thank you. Okay, thank you.
A small gift for you. Thank you.
Thank you.
Thank you very much.
Thanks. Thanks, okay.
Okay, as I said, today tea is being served in the Homi Baba cafeteria, which is just when you leave the
No, no.